All right, kids, let's talk about the multipole expansion. I mean adults, young adults, younger people. Okay, so the multipole expansion is a way to approximate potentials at large distances. So we can think about if we have no charge, then we have no potential. What if we have plus q and minus q? So that technically in this area we have zero net charge. What does the potential look like? It's really interesting because we can calculate what that is, and that's called a dipole. So we have one plus charge and one minus charge, and we want to know what's the potential out here due to those two charge configurations, because that's the whole thing of E&M is what's the electric field generated by charges. That's all you're doing all the time. Okay, so how we do that? Simple. We calculate the potential from that charge, and then we calculate the potential from that charge, and we add them together. Since it's plus q and minus q, the potential for a point charge, distance r away, is 1 over 4 pi epsilon naught times q over r. And if you add them together, you get plus q and plus a negative q, so you get this minus q on there. And so you have 1 over 4 pi epsilon naught times q over r plus, and then minus 1 over 4 pi epsilon naught q over r minus. Okay, and so this would technically be plus, but your charge is negative, so you can bring that minus sign to here. And then you've got this and that. You factor them out front, and then you have q over r plus minus q over r minus there. Okay, and so that's our net thing. Okay, so far so good. Now all we have to do is put this in a different form so that it's maybe independent of two r variables, and let's maybe try and put it in terms of the separation distance between the charges. How about? And then how far away we are from the center of it. So maybe in terms of r and d, maybe that'll be easier. So if we want to figure out what r plus is in terms of, say, this distance, which we can call d over 2, and this distance r, we can use the law of cosines, which relates d over 2, r, and r. And we get that the r plus length here is equal to r squared plus d over 2 squared, and then minus this component rd cosine theta, and then that it's the same for r minus here. It's just we have a minus sign instead of a plus sign. Okay, so then you get, this is just the law of cosines, and then we do some factoring to pull an r squared out so that you get 1 here, d over 2, and then r squared, and so on. And this, so that's where this comes from, is by factoring out an r squared from everything. And then you can square root everything, and then you get an r, and then you can invert everything. And so that's where this comes from, is by taking the square root of everything. So you get this to the half power, and then you invert it to get it to the minus half power, and that's where this minus half comes from. So then you get 1 over r plus and minus is approximately equal to 1 over r times 1 minus d over r cosine theta. So we're putting this in terms of this distance and that distance. Okay, and this distance here is approximately 1 over r plus or times 1 minus d over r cosine theta, this angle of the theta, okay? Because what are we trying to do? We're trying to get a different form, and so we're getting 1 over r plus here, and that's what we're trying to do here, okay? So this 1 over r plus is approximately 1 over r times this thing. And then this is approximately equal to, because of the binomial expansion, which says that if you have a number of the form 1 plus x to the nth power, this is approximately equal to 1 plus n times x. Okay, in this case, our n is minus a half, and our x is d over r cosine theta. So if we take minus a half times d over r cosine theta, we get d over 2r cosine theta, and we get a minus sign on that. And so that's where this comes from here. The minus plus flips to a plus minus because of the minus a half. So this is 1 plus x times n, and the n here is a half, and it's a negative a half, so it flips it there. Okay, and then you do that for both the plus and the minus r, and so you end up with this expression here, because what you can do is say that 1 over r plus is equal to 1 over r times 1 plus d over 2r cosine theta, and then 1 over r minus is equal to 1 over r times 1 minus d over 2r cosine theta. Okay, and if you carry this through, 1 over r minus is equal to 1 over r minus d over 2r squared cosine theta. Just factor that all through. And so then you get that 1 over r is equal to 1 over r minus plus d over 2r squared cosine theta. Okay, and then you have what 1 over r is, and you can go back to this expression, plug that in for 1 over r, and then you can get that 1 over r plus is equal to 1 over r minus plus d over 2r squared cosine theta times all this stuff, and then you can, do another substitution and keep going and simplifying that to an even simpler problem, because I said so. Yes, I think they just have to do that a couple more steps of algebra. Okay, and then what you end up getting is this expression here, 1 over r plus minus 1 over r minus, and then on the other side of the equation you have your simplification. Okay, so what's the point? So we're trying to see how this potential behaves as a function of the separation d between them and this angle. As we sweep around out here, what does the potential look like? And it turns out that if we replace this with this, because this is the same as q over 4 pi epsilon naught times 1 over r plus minus 1 over r minus, okay, and we just found out what that is. So that's d over r squared cosine theta. So then our overall potential is just here, 1 over 4 pi epsilon naught times q, and then times this d over r squared cosine theta. And so that's where all this comes from. So the potential of a dipole, which is what we just solved, goes like 1 over r squared instead of 1 over r. Okay, so it falls off a little more rapidly than a point charge. If we put together the pair of them and we make a quadrupole or an octupole, we get just increasingly orders of r. So we have 1 over r for a monopole, 1 over r squared for a dipole, 1 over r cubed for a quadrupole, and 1 over r to the 4th power for an octupole. Okay, these are, as we keep going more and more and more, we get the monopole, the dipole term, the quadrupole term, and so on. Question is, though, that's a very specific charge configuration. What about if we have any charge configuration, any localized charge distribution? Localized meaning it's, confined to an area. What would the potential look like really far away? Okay, and so then we have our potential is defined as 1 over 4 pi epsilon naught times the integral of the charge density over the area of concern and then over r. Okay, and we can use the law of cosines to then, again, put our r squared into some generic, r squared plus r prime squared minus 2r prime cosine alpha, blah, blah, blah. And then alpha is this angle between r and r prime, okay? And then we can write r in terms of the magnitude r here times the square root of 1 plus epsilon, where epsilon is this defined to be this ratio. And then for points well outside the charge distribution, epsilon is much less than 1. Okay, and then so if that's the case, again, you have your binomial expansion, and he goes a few more orders of terms, 1 minus a half epsilon plus 3/8 epsilon squared minus 5/16 epsilon squared, and so on, adds it up, and then he keeps going with some algebra to collect the terms. And then this thing, if we look at it, the coefficients, all these terms in parentheses, are the Legendre polynomials. And this result is that 1 over r, script r, is equal to 1 over r, the distance. So script r is the distance from some point charge, and then r is from the center of the charge distribution. And 1 over script r is just 1 over r times the sum of the Legendre polynomials, okay? So substituting that back into 3.91, you get this nasty thing, which says that the potential of any charge distribution is the integral of the charge distribution, and then the sum of all the little r values. Okay, so more explicitly, if you want to write this out, you get the potential is 1 over 4 pi epsilon naught times 1 over r. So this is the n equals 0 term. So n equals 0, you got r prime to the 0, which is r. and then, or sorry, it's 1 times P0 of cosine alpha, okay? And we'd have to go back to the polynomials to look up what P0 is, but P0 of cosine alpha is just 1, and then times rho. Okay, so that's why this first term, 1 over r to the 0, is 1 over r times just the charge density. And that's your monopole term. That's your normal, what's the potential of a point charge. And then for r equals, or n equals 1, then you have 1 plus 1, so 1 over r squared, and that's where that comes from, times the integral of r prime to the 1. So then you get your r prime there, and then p1 of cosine alpha is defined to be cosine of alpha, and so you have, or just x, so p1 of x is equal to x, and so in this case x is cosine of alpha, so then we just have cosine alpha times this, okay, and same thing, r to n equals 2, you got 1 over r cubed, and so on. And so this is the Legendre polynomial, this is the n equals 2 Legendre polynomial, and we can go back up and look at the Legendre polynomials. I believe they are not too far back, if I remember correctly. And look at the list of the here you go. So these are Legendre polynomials, and P0 of x is 1, P1 is x, P2 is 3x squared over minus 1. So we had P0 of cosine alpha, where that's what our x is, cosine alpha. So P0 is 1, P0 of cosine alpha, not P0, but P1 of cosine alpha is x, or is the argument. We call this whole thing the argument, so we get cosine of alpha here. And then P2 of cosine alpha is equal to 3 cosine squared x, or alpha, sorry, minus 1 over 2, okay, and so on. And so that's where those values come from when we were talking about them a little bit ago. Okay, so go back down to where we were. Okie dokie. So the multipole expansion. So that's what this is. Now, so it's the sum of all the integrals, okay? So we go back here. So this plus 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 this, all of these things added together, and then the integrals of all of them added up. The integrals over those spaces added up. So for all those little things, okay, all those little areas. So this is called the multipole expansion, okay? And the exact, or an example of that is to do this thing. You can use the fact that this multipole expansion, if we want to find the approximate potential for points on the z-axis. So let's say you take the first 3 terms for this potential. So we've got the first term, the second term, and the third term here. Let's say you want to do this problem. So you're going to have v of r is equal to 1 over 4 pi epsilon naught times 1 over r times the integral of our charge density, which is this mess. So we're going to have k r over r squared times r minus 2r, and then we've got a sine of theta, and then we're going to do this in spherical coordinates because they gave it to us here. So we're going to have an r squared dr, and then a sine theta d theta, and then we'll have a d phi in there too, and then you'll do this integral. Again, what you'll see, if you do this integral, you can do the r first, or the theta first, or the phi first, whichever one you want to do first. 3 integrals, okay, and then you're going to see that if any one of them are 0, then your whole potential is 0, or at least for that one contribution, because that's just this part of it. The next integral, so we're going to add the next sum to it, and that's 1 over r squared, 1 over r squared times the integral of r prime cosine, in this case alpha is theta, or in our problem we're defining theta to be this alpha variable. So cosine alpha times our density function, so we have k r over r squared, r minus 2r, 2r, and then sine squared theta, blah, 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 blah. Okay, so you get the same thing, you keep going, and what you find is that the first 2 are 0, and the third one is a non-zero answer, and that's your approximation of what the potential looks like for that charge distribution. So that's pretty cool. We can take any charge distribution. Look at this. What kind of charge distribution is that? Any charge distribution, and we can figure out approximately what it is. And so that's called the monopole expansion. And that's, just a way to determine the, sorry, did I say monopole? The multipole expansion. How to determine the approximate potential generated by any charge distribution as long as you're sufficiently far away. Okay, so that's pretty cool. Pretty cool. So the monopole and dipole terms, the monopole term is 1 over 4 pi epsilon naught q over r. And in this case, q is always the integral of the charge. So it's your total charge, okay? Blah, blah, blah. Let's see. And yeah, so the integral here is called the dipole moment. So if you integrate r times the charge density of r, this is called the dipole moment. And then you can change your, dipole integral here, and this integral turns into something we call the dipole moment, and then you have p dot r hat there, and then there's no integral anymore because our p holds the integral information, and that's called the dipole moment, okay? If you have a collection of point charges, it's just the sum of the point charges times this r, the separation r vector between them. And then for a physical dipole, it's just simply qd, which is kind of cool. So this is what you have to take away from this, your most common thing that you're going to have to deal with. When we talk about dipoles, if you want to know the dipole moment, it's just q times d. Okay, and q times d, again, for a dipole, if we go back to the dipole moment, here it is 1 over 4 pi epsilon naught, and then p, or qd here in this case, and then cosine theta over r squared. That's where that, another way to think of that problem. Okay, so then p dot r over r squared. Okay, and that's what p dot r is in this case is qd and then cosine theta and then over r squared. So that's, if you're wondering where that all comes from, that's another way that we talked about the dipole. Okay, so that's your dipole moment. And so what you care about is just remembering for a dipole that a dipole, physical dipole, has this qd value in it. Okie dokie. And then we've got our coordinates here in our monopole, our multipole expansion problems. And this is just having to do with if you shift your coordinate systems around, showing you that there's kind of a dependence on the coordinate system, but you can recast it in an independent coordinate system if you are clever. So then, yeah, with respect to what origin is the question here. So, yeah, read that. 3.4.4, the electric field of a dipole. Okay, so then for a dipole, if you, we've talked about the potentials, but now what if you want to know the electric field of a dipole? If we choose the coordinates so that P is at the origin and points in the z direction, which is this thing, so your dipole moment is up, and so then r dot p is p cosine theta over 4 pi epsilon naught r squared, then that's our dipole, and p is qd, but we can keep it as p for the moment. So to get the field, we take del v, okay, and then we do it in spherical coordinates. So you get e r, e theta, e phi, and then if you do that, you take the derivative with respect to r, with respect to theta, with respect to phi, and then you get that it's just an r and theta components, just has r and theta components, and that's the electric field of that. And so there you go, there's your electric field of a dipole, which is pretty cool. And if we, if you want, you should go to math3d.org and type in this potential and see if it looks like what it looks like here. Okay, and that's the electric field generated by a dipole, which if you've done the E&M lab where you try to sketch this thing, it should look a little familiar. Okay, and then that's the end there. So that's pretty cool. You're just estimating V, the potential V, and then this last part is calculating the electric field from there, which is just taking the gradient of it, which is pretty cool. Okay, and so those are just some techniques. So what are you worried about? Just make sure you understand the dipole, and that the dipole moment for a dipole is Q times the separation vector D. And it's the, D is in the direction between the two charges, okay? And it points from the -1 to the +1. So that's a really important thing. And figure 3.29, that's what this D vector is always pointing in that way, that direction, okay? And so that's what your dipole moment is in the direction of the dipole. Okay, it's pointing towards the positive charge. Okay, so if I had my dipole like this, and this is my plus charge and minus charge, then whoop, there's my dipole, there's my P vector, okay? Okay, that's it. Talk to you guys later. Boo.